So hello, yeah, please let me know if you can hear me well, and also let me know if the screen size is okay, because at least I see that in my small window for the YouTube that it might not be okay, but let me know if the screen size is okay, if the audio is okay, and yeah, just let me know who you are here, what students are joining today, and what about the screen size? Can you see the whole screen? Hopefully. Okay, that's good to know that the screen is okay. Then it's just my browser is a little bit choppy. So, okay, the first thing is that please go to the Google Classroom and download the dataset that I provided. So that dataset will be about the radiology, you know, like for selecting the lungs. So I will also drop it here in the chat. So please let me know when the file is downloaded, and also yeah, let's download the file, and then we'll move on. Also, while you're doing that, I can show that the Christophers have finished the homework last time, really good one. So I did not examine the details, but in general, the idea was that he added two types of vector. So with the embeddings of the numbers that are with the class of 3 and the embeddings of the numbers with the class of 6, and then he generated, using the variational autoencoder, the outputs, and you can see that many of them resemble 8, right? So they are not perfect, but they are, I think, really good work. And also Christopher has had some problems of loading the pre-trained weights. I just checked with Pytorch 1.7 and it works for me. Not sure exactly which part was not working. So if somebody have problems with that, then let me know. I can help you out. So Christopher did this himself, so that's really great. Also, he even tried with the balls dataset, so the synthetic one. So he selected the blue balls and then passed to the variational autoencoder, and you see that most of the outputs also are blue. They are not perfect. The autoencoder itself was not trained to be perfect. So that's really good job from Christopher's. I encourage others also to try out that homework. Then yeah, that was generative model, basically, with also the ability to use vector arithmetics. And today we have the task of semantic segmentation. So that's one. So there are the semantic segmentation and instance segmentation. So the difference is that the semantic segmentation, if you look at this picture, so this is again something that is commonly used for the let's say self-driving cars and all sorts of navigation tasks and so many other things, like very popular thing. So yeah, so I see that some of you already downloaded the dataset. So just a second, I will write down. So is dataset ready? And meanwhile, I will explain a few things. So plus, minus. So as you see here, there is a vehicle class. So this is also interesting that you can segmentate out as many classes as you want. So in this case, there are 8 classes. You can also segment just one class, as you will do in a moment. And but you can see that the vehicles, at least for example here, they're all as like a one blob. So basically, if we would use the blob detectors, like in OpenCV, we would get one vehicle here. But actually, if you look at here, there is one vehicle, the second vehicle, and the third vehicle. So that if you want to select separate parts of those vehicles, then you would use the instance segmentation. But for many tasks, semantic segmentation is okay. Plus, it's also very per pixel friendly, so there's a lot of ways how you can use it to have higher accuracy per pixel. If it's not important, if you just need the bounding boxes, then probably semantic segmentation is not the best thing. And yeah, so but in many tasks, actually the per pixel precision is quite important. So let me then show you the dataset that we're going to work today. To load the dataset, it's really simple because you can just, you know, like you can just load this numpy array by np.load, and it will you don't even need to know the shape of the array. Everything will be provided for you. But let me quickly find the samples. So I took some samples out of that dataset. I think this is from Kaggle for the segmentation of the lungs. So you can detect some abnormalities and also calculate the area of the lungs. If you have like good segmentator, you know, like you can calculate what is the percentage of that area and if there are some defects. So this is going to be the input and this is going to be the output. So the output mask will be what we want to predict, where is the lungs. Of course, you can later at home try out to use something like this. In the Torch Vision, they have a couple of datasets like these, but they are a little bit heavier. So for the tasks of online coding, we should not use that heavy dataset. So here then, if you look at the papers that I shared you, so this is one from 2015. This is original UNet. Then they later had UNet++, I think, the different authors, and then UNet 3 plus now, and then there is also Deep Lab and others that you can try out. So here the architecture, it looks like this. So we already know how to make dense nets, res nets, so this is something very similar to what we had before actually. The only difference is that the skip connections now go not only within the res blocks. So basically these parts in between, they could be convolutions, but they could also be res blocks. But the most important thing is that you have skip connections from the encoder part to the decoder part. So you already know how to create autoencoders, right? You already know how to create res nets. You already know how to create dense nets. So now all of this is coming together to make the UNet. And with the UNet, we like the first implementation that we're gonna make, and also I think that was in the reference paper, is that we're gonna select these feature maps from this layer and concatenate those feature maps to the end layer here. And then we'll have at the end this segmentation map. And we're gonna train that with a specific loss function. So let's start with some questions. So let's start with the most easiest question. So if we have this kind of data set and we have semantic segmentation model that needs to predict where in this image is the lungs. So what kind of loss function should we use? What loss function should we use? This is super simple question. So if you think that in the, okay, I was not asking for the plus, but still, like, what kind of loss function should we use? And so here, what we can interpret, so that maybe I will not say ahead of the time, but we'll see. Root mean square error. So this is, you could use that, but this would be so bad. You should, so the root mean square error, I know Christopher's referred to that most likely because he himself works in research with that kind of metric, but this is a metric. Remember that metrics can be your loss functions, but they also can be to evaluate the results, and this is very bad loss function. Maybe you have some better ideas. So let's see. So the map here, what it actually is is, so let me check what was the actual size of that map. Just a second. And meanwhile, you can try to give some other ideas of the loss functions. I will double check what was the size of that. Just a second, that's going to be fast. Forgot to look at the size of the input. So I have only one idea now, but we have 7 people here. So Kirill is doing something that is good. He's looking at the paper and reading it. That is not bad, but so still we don't have the winning answer. Nobody has yet given the winning answer. So the inputs are actually 1 by 256 by 256. And if you look at the image, of course, the inputs will always be in the range of 0 to 1, and the more precisely, it will be only 0 or 1. There's not going to be any other kind of input, because it's like either it is a long or it is not a long. So, but we're still missing the loss function. So what loss function should we use? Still no correct answers yet. Do you have any ideas so far? Meanwhile, I will type the loss function myself, but in general, like if you see that kind of shape and that kind of constraints to the data, you should immediately guess the loss function, and you already used it many times, in my opinion. So let's see. This is going to be sum over something. What was the so no answer still, yeah. So maybe I will need to then give it to you. So let's wait a few seconds while I'm typing it. Maybe somebody come up with an answer. So like that. And then we also would prefer to have weights there. But let's see, what was the control sequence? And still no answers. Interesting. Just a second. That is unexpected. I would think that some of you should be able to give the answer to this question. So, okay, so if you see, we get right, finally. Maybe this is because of delay of the YouTube live, because yeah, immediately 2 people came up with the correct answer. So if you have only one output that is always 0 or 1, that automatically means that you could assume that that is a probability, and if you have just one output, then you don't need a categorical cross-entropy. You would need only binary cross-entropy that have the nice benefit of having the opposite side of the probability included in the loss function without using a softmax or anything in between. And yeah, so that is one thing. So the next question. So why would you think that these skip connections are beneficial? So if, for example, we would train the same task with the autoencoder that I showed you 2 sessions ago, why would we not get that good results as using this technique? What do you think? So why UNet skips are good addition? So why do you think knowing the structures and the way how these function graphs work, why do you think these skip connections are a good thing for the semantic segmentation tasks? Do you have any ideas? If you don't have any ideas, you can type in minus. No ideas is minus. So I see that we have people on the stream. So hopefully you should be able to give some idea of this. So let's wait for a minute, and then we'll start with our first task today. Just a second. Meanwhile, I will look up the task. I will even open it. So the first task will gonna be to actually implement the forward pass of the UNet, but I'm still waiting the answer for the question, hopefully. So let's see, that's why I'm gonna share this one. Okay, I see some answers at least. So, because you lose higher resolution information when you downscale, when skip connections, you get the higher resolution information back. This is the main reason why segments, why it is so precise and higher resolutions. Right, this is not bad answer in general. So there is one mathematical reason why you always like skip connections. They are like hacks for the backprop gradients, so that they would not disappear or vanish, because as like a deeper model you create, and there is if you don't have specific procedures for regularization or some kind of optimization kind of restrictions, then the gradient would be lost very quickly. And if there is even the in the middle the small bottleneck, so all of this high resolution information, as Christopher is saying, is encoded in this small bottleneck vector. So it's kind of really hard then to deconstruct it. But what you can do with skip connections is basically just copy the high detailness of the input image directly to the output image, and then apply your model basically as a filter, and then you get out really nice images and per pixel precision. So now I opened the task in the Jamboard in the Google Classroom 15.2, and I also will drop the link to the template here. This is the template link. And also I will drop in the task. So please start doing it. I will also show it a little bit. And then we'll see who gets this done first. It'll be interesting to see how well you are able to do this. So here will be also the model structure, model equation, basically. The initialization part is already given, so that's going to be easier task for you. You just need to implement the forward pass. And if I add the, just a second, the actual function graph. So the function graph is really simple one in this case, like this. Oh, there is some bugs with these lines. Just a second, I will fix them. At least in the Jamboard, I will fix them. So there should not be that 8 and 4 for not. I think that was because there should be coefficients, not those bottom subscripts. Just a second. But still, you can start implementing it. Just a second, just a second. Where are my code? I got lost in my LaTeX equations. So, what is that 8 for? That's a little bit strange. Just a second. I will produce the correct equation for you, not the incorrect ones. So, as you know, all of these function graphs can be displayed as a nice pictures of the, let's say, schemas or graphs, but you can also display them as equations. And sometimes I actually prefer equations, then it's a little bit clearer, because with the visual things you can mess up something. So, okay, let me add a little bit corrected version. Not sure why there were those strange things. So this is gonna be the form cat. If something is not clear in that equation, please let me know and I can explain it to you. Because otherwise, when you will be stuck alone doing those equations, then it will not be that nice if somebody cannot explain it. So yeah, let me know if I need to explain it. I think it's quite simple, like it should be real simple. Okay, so let me share the code as well. So if we go now in the code, so we have dataset longs. So you need to show your location to your dataset here, of course. Maybe you can just extract it in the same place where you have your code. Then if you go down here, there is a res block that we know how to make with the bottleneck connection as well, where you can change the output channels as well, not only just without changing the channel count. Then here we have the res blocks, right? All of them. And we also have the other part of the up convolutions, or let's say they are also res blocks. And if you look here inside these res blocks, they are quite fancy ones. They have group norms. So this is already patch size independent. That is really something that we encourage you to do right now. Everybody uses group norms now. Then we also have the upscales as a bilinear upscale. So that's also a nice method to use, not to use some kind of pooling, max pooling or something like that. Also for downscaling, basically you could use that. So yeah, for downscaling we use actually max pool, but we could use also we could use actually also some downscaling using the bilinear, I believe. But let's stick with this architecture, right? I just don't want to change the equation. So if you look at the Jamboard, we need to implement here the equations. Everything is already given to you. It's super simple. And here you also need to implement the loss function. So I forgot actually add this to do, but you need to implement the loss function as well. So you already know what kind of loss function you need to implement, and you know this part as well. So I'll let you try to do this yourself. I believe at least most of you should be able to do this quite quickly. Yeah. So I will give you, let's say, 5 to 10 minutes, maybe 10 minutes, and well, if you have some questions, then type in the chat. Yeah. Yep. So I will move back to the Jamboard. Yeah. Let's see who's going to be the first one. holding the coding competition in deep learning. So how are we doing? I see that nobody yet submitted the code. Okay, let's do some test questions. So, are you trying to finish task, or given up, plus minus? So that would be a little bit valuable information for me, just not to sit around and wait for somebody to finish the tasks if you're all given up. So hopefully you're not given up, but let's see. So I see some questions. I just realized actually that I think with the loss function, with binary cross-entropy, I forgot maybe a minus sign, but that doesn't matter because you can flip it around, you know, like to maximize or minimize. But in general, so I see also some other questions. Yeah, I've forgotten a minus sign in the front of the cross entropy that you can do. But so there's somebody asking, what is that sign? Of course, that is sigmoid. Yes. So at least two people could not recognize the sigmoid. Okay, but yeah, that is sigmoid. And actually maybe I can help you out with that. So the way how I can help you out with that is using one nice tool. So that is, especially when you write in LaTeX things, the Textify, there is one really nice tool that's called the Textify, where you can draw in some kind of those symbols that you're not sure what they are actually. So if you draw in this one, you'll get it's sigma, and basically it's sigma, of course, that's sigmoid. So, and also there's another way how to understand why you should have sigmoid there is just because that of course like if that is binary cross entropy, what else you would put there, you know, like that's quite obvious, you know. So okay, I see that you're racing towards who's going to be the first one. So I will let you do that and let you know how are you succeeding. Oh no, yes, I forgot to warn you. There is one library missing for maybe for some of you. Just a second. Oh man, that I forgot. Really sorry for that. But you can easily fix it by installing using the pip. That's quite should be done quite easily. So we'll look up with the things. Just a second. So if I go here, so one thing that's missing for some of you is TQDM. So that is like just a console tool. So you can use pip install TDQM and you can have it here from the terminal. You can press on the terminal button and then just install it here. Or another way you can do this is just to comment this out. If you comment it out there, you can also comment it out here by having just leaving it like this. So it will work either way, but it's just like a progress bar to improve the output. So here the Y prim is missing. You're right, but you should be able be able to do this yourself. You know, I can give you this small line, but this is something that if you did these models many times, this is like super simple stuff. You know, forward and forward and give the X in, right? So this is no brainer. You know, you can get Y prim without asking it. So, but of course you can look up as well here, but hopefully you should be able to do this yourself. So let's wait for somebody to hand in to this task, and then I start showing you the answer. So the Y prim is also here. The T, Q, D, M options I also showed what you can do. So if there's some other questions, you can ask as well, and let's wait for who's going to be the first one. So I don't see anyone yet finished it. That's very interesting. Maybe if you have some other problems, you can type in chat. Actually, before I think some of you already quickly exchanged with some answers. Maybe I don't know about some other problem that I missed. So let me know if there is some problems. Yeah, so it's really interesting that I did not get yet any completed result, but I will start slowly showing the answer. Hopefully some of you can submit result before I complete my code. So let me see. So if I share the code now, so I already shared the code, right? It's actually open all the time. Great. So the loss function, that's the most primitive thing ever. So just, yeah, so minus torch. I could use sum, I can use mean, as you know, we already talked about it many times. So the mean is learning rate invariant and the sum is not, but the sum is a little bit simpler function. Sometimes works slightly, like in general, it should not have much difference. So here then will be the y times torch log of the y prim plus some epsilon, of course, then plus 1 minus y, and then the same thing again, multiplied by, whoops, 1 minus y prim. Hopefully that should be okay. Here's a loss function, right? So the loss function should be okay, hopefully. So I'll add that also to the Jamboard, and if I will have some mistake, then I will update it again. But let's see. So starting to add some answers to the Jamboard, and I will also check if somebody is actually completed this himself before me. So I'm adding this here. Let's see. We still don't have any handed in as results. That's too bad. But let's keep working on it. So, okay, the loss function should be okay. Then we are starting to do the equation. So then let's see with the equation. So we have, let me actually open the equation so that I don't need to switch between the windows. So I have it. I can even have the same notation. So out, maybe I have a mistake there. If I will have a mistake, then that's going to be my fault that you did not submit this task, but let's see. Hopefully not. So then the convolution forward of x, that is out 1, out 2, again not so difficult, to so Kirill asking question about what we do with the skip connections. So if you look at the equation, it already tells you what to do. So the notation of these square brackets, very common notation, that is not addition. And also you can use this, what was the deduction method of logic. If you see that there is no plus signs, no additions, then of course that is concatenation. And you also can you can look at the res block configurations here and see that here in the up 4 you have 128, and you can think of that as well. Why would this would be different if there should be additions? Right? All of those hints should kind of give you the answer to your question. So hopefully you can come up with this yourself. So then out is here the 1. So then out 2 from 3, then here will be the 3. Then out 4 is without the max pool, I guess, right? So we don't use the max pool for that one. In general, those max pool and upsample can also be written only in the forward pass without predefining them, because there is no parameters to learn, but you can also do it as that. So it's just like if you have written it before, maybe it's easier to look at it. So here is the out 3, out 4, then we have the middle part, right? So this is going to be the mid, and here is going to be the out con mid, middle, this one, right? Now starts the fun part. So out 6, and we'll see if we have some bugs or not. Let's see. Self upsample forward. Let me also check if somebody finished the task before me. Seems like that nobody finished the task before me yet. Let's double check. Nope. Okay, maybe that could signal that I have some bug in equation, but let's see. So then the up convolution of 4, basically the changing the channels down, so that would be the channels down convolution. So here we have the torch cat, right? So the torch cat we also used already in DenseNet. We used it quite many times already, so that should not be that big of a surprise. So dim, the dimension where what we want to concat is not the batch size, but we want to concatenate the channels, of course. So we use the dimension of 1. Then we'll choose what we're gonna concatenate together, out 5. So something is missing here. Okay, this was the missing part, I guess. Out 5. So here the out 5. We concatenate with out 4. Right. So just to make sure that so far all of this is correct, I will add the breakpoint here and run it as a debug mode, just to check that I don't have some bugs in the equation so far. It could be that I have as well, but let's see, hopefully not. Yeah, so seems like maybe that is the reason why you did not complete it. Oh no, something, because it should not be a bug here, but something is not working, but we'll find it out. Maybe that was my fault. So the model, correct. Then here in the line of 110, we should pass it to the convolution. Okay, I missed here. I think there should be number 4. So very easy to mess up. There should be 4. Again, running again. Even with the equation in front of me, easy to mess up. So let's see. Yeah, it works. So far it works. So no bugs in the equation. It seems like so far. Also, nobody has finished it. Interesting. It's a little bit scary. Hopefully that I don't have some significant bug onwards later. So let's keep writing it out. So then the next line, 7. Then the up convolution 3. Then the inputs are 6 and 3. Then then the next one, 8. Then the inputs 7 and 2. And here is going to be also 2. And then we have the y prim. The y prim is going to be the torch sigmoid of the up conv 1 of the forward pass of the concatenated equation of the 8 and 1. 8 and 1. So let's see that I don't have bugs so far. Many times I do have bugs, so sorry for that. Hopefully not this time. but we also know how to fix it. So the upsample of 3, so I guess maybe we found a bug. That's probably because that's why probably you did not submit all of the stuff. We'll see. So let's start analyzing the situation. So out 6 size. This is 16 by 32. Okay, 32. Okay, that's the important number. 32. Then what we have here is the up column 3. That should be 64. Sorry, that is correct. This out 3 should be 32. That is correct. So far correct. Then what is the problem there? If I copy this line in the debugger, dimensions doesn't match. Okay, the width and height dimensions are not correct ones for the out 3. Okay, so I had a bug. Sorry for that. I had a bug here. So the out dimensions in the 6th one and then in the 3rd one a little bit different. So here this is upscaled here. Probably the upscaling stuff is a little bit in the wrong order. No problem. We'll quickly fix it. Sorry for, I guess the equation was a little bit wrong. Let's see. So let me look and think which one should we upscale and which one we should not upscale. So I think we should just upscale the one that is coming out of the output. So this is gonna be this one, the out 6. So let's try upscaling only out 6. So if I remove some of those parentheses, okay, so this is actually upscaled already. So this is upscaled already. This is upscaled already. Then I guess we could upscale the out 7 here. Oh no, but this is correct. We should upscale this one. Haha, something is not adding up. Which one should we choose to upscale? Just a second, that's not going to be too difficult. So this one, out 6, is then, maybe I started to upscale too soon. So let's check if I remove this first upscale off. Then we have 1, 2, 3 downscales, but we don't have 1, 2, 3 upscales. Upscale. I guess we could upscale. I think it's not going to be enough. We'll need to upscale once more, but that's no problem. We'll think how to do this better. So the out prim, let's see, the X size is 256. Y prim size. Okay, my equation was not great. Yeah, that's right. We need one more upscaling. One more upscaling. So if I have upscale there, then the max pool of that one, then I don't want actually to have the upscale before the last one. Sorry for that. Maybe some of you definitely can come up with your own solution for this small problem, but I will quickly find one that works for me. So here, the upscale of this one, we can leave it as it was, but it is now combining the 4 and 5, and then it will be combining third. So the third will not be that shape. Okay, I don't like it. I don't like it. Okay, my equation really bad one. Sorry for that. So here, before the last one, maybe we could do something interesting at the end. So we have the upsamples. Sample out 6, right 5, 4. I don't want to have the upsample just before the output. Definitely don't want to do that. They actually also don't want to have 2 upsamples, that's for sure. So probably you just need to change the place for the upsampling. Yeah, definitely. It'll go somewhere inside here. So we'll see. So then the third one is from that max pool. So it probably means that I should upscale the 6th one, but let's see. So if I add the breakpoint here, the upscale operation was in the wrong place in my mind. So let's see. So if I have this one is 32, this is 32. Okay, that's fine. Then what about the 4? So that actually also was working fine. I guess I collected the out from the wrong place. Okay, I see that Lee actually submitted. Oh no, Christopher submitted his version. But I just don't want to break the function graph. Let's see what he come up with there. Of course, yeah, he broke the graph in having the pools outside of the axis. That's right. That is one way how to do this. I'm just thinking if I have some way to avoid that. I guess I don't have that way, at least just without changing the actual model. So yeah, probably we'll need to do it the same way as Christopher's did. So here what we can do is I think we can just change a little bit around these things. So one is we can leave this one as out1. So this is going to be out1. Then here the out1, when we give it in that layer, we will call maxpool after that one. Then again maxpool will call after that one. Then again we will call maxpool after that one. Like that. So now we have those outs in a different order. And now we also will need to change the ins in different order. And then I will update the equation so that it will be correct one. So this part is now looking much better, hopefully. Yes, it worked so far. So the out5, then let's look at these guys. So out5 is 32. Out4 is 32. Okay, so that's fine. Then so that's going to be actually yeah, this is going to be 32. Then here the out 3, what we would like to add should be 2 times bigger, I think. Yeah, it's 64, so that's great. So what we can do is to shift around those upsamples and max pools to have it a little bit different way. So adding here the max pool, adding here the the upsample, and also to what is not liking it here. Something is not great. What it doesn't like. Okay, so this one, and then the last one is here, I think. So now should work, hopefully. I messed a little bit up the equation, and then I was thinking, why are you not giving the result? That is typical, very bad situation. So let's see. Yes, it works, and the output is in the correct shape, so that's great. So I'll let you see this part of the code, and I will immediately also fix the equation. So I'm fixing the equation in LaTeX. So maybe I can even show you how I fix the equation, so you can see in the LaTeX how you write those equations. Full screen sharing, right? So if I generate the code, now this is not exactly correct now. Or what it actually should have is then from the first convolution nothing should be changed in regards to the dimensions of the width and height. But then for the next one, it should come with the inner part, not the outer part, that I made mistake here and here. And then in the fourth one as well, like that. So if I text it, so it's a little bit different now. Okay, let me see why it's so big. Okay, let's see. No. Okay, I cannot minimize it, sorry. So, okay, so that part with the max pools should be okay then, the third one. And then the upsampling. The upsampling is also a little bit wrong. So those should come in the 6th, 7th, and 8th. So I delete it here, add it here, like that, and here as well. So you can double check if my equation now is correct. So, yeah. Okay, out, deconv. Okay, cool. So hopefully now the equation is okay. So I will share that in the Jamboard to fix the previous one. Really sorry for making you work on something that was not correct in the equation. As you see, quite easy to mess up these kind of things in sense of just writing the equation and then realizing that it was in the wrong order a little bit. So I will also add the code, and then we'll move on to the next task. The next task will not going to be too difficult. You will need to modify your code a little bit. So meanwhile, you can try to finish this one. And for the next task, I suggest you that you copy your file and don't just destroy the code you just made. So, and maybe I will, before that one, I will also show how it actually works. So, oh, nice. Jans Hoffman is also giving good comments. You're right. There are great ways how to improve these things using even dilated convolutional layers and other things. Now we are doing the baby steps, but yes, the state-of-the-art models are a little bit complex. In general, I would say that, so I'm right now running the training just to show a little bit the example of how it actually works. Like from my experience right now with semantic segmentation, I would prefer using the UNet 3 Plus with this GCM layer. So I think they don't use dilated convolutions, but I would say that probably, as you say, in some cases they are very beneficial. I don't know that theory that well. If you can share some paper or references where they prove that they are very good, that could be great. So now, just a second, this will finish, and you will see some results, and you can catch up with the code. And I will quickly then share the next task. So now the test code. Okay, so see, so it looks like that. You have the lungs and there is a actual ground truth and then the predicted sample, and we don't shuffle the test set, so you can get the same images seen like progressively after every epoch. And you can also see the loss metrics. Of course, the loss metrics and the other metrics for the semantic segmentation, there are some of them that we will quickly look at the end of this session. It's not only just the loss that you usually look at here. So just quickly, let me fix the equation for the next task, because there is also this bug with the incorrect locations of these upsampling and downsampling. Sorry for that. This will be quickly, because you will see that the next task will be really easy one in a sense of equation. Maybe it will not be that easy to quickly change the code, because it's not just few lines. You will need also a little bit think about it. So the one thing that I know is in the papers that they're discussing sometimes is that either you should use the dense-net type of thing of the concatenation, or you should use the ResNet type of thing with the addition. So the addition have the benefit of the derivatives having to be this equal in the both arms of the equation. But the concatenation have some other benefits of adding more details to the like copying exactly those details to the outputs. And here and then there is also the fishnet actually, where you have both of them together. But here, let's say the next task will be to 5.3 to implement to change your code. Let's copy your code and make it to have with the additions. So not the concatenations, but additions. And this task is not like super simple. At the same time, it is super simple, but it's not like you don't need just to change those the concatenations to additions. You need to think a little bit more what else you need to change, and then submit the code. Hopefully this time there will not be a mistake in the equation. At least there should not be, and you should be able to finish it yourself this time. So I am slowly opening the task in the Google Classroom. That was really a fail before, that I did not see that there is a problem in that equation. But hopefully now it's resolved. So 5.3 task, this one, 15.3, sorry. So let me know how are you doing with this task, and in a few minutes I will help you out completing it, because we're already a little bit late than some other times we are. So the previous task is finished by a few people, so that's great. This task, the new task, is also open. Let's see who gonna finish that one first. I think I also had some kind of bug in one line with regards to metrics. Interesting. Metrics, append. Right. There is a small bug because I wanted to make it a little, so you should not have this line of 180. So I had originally planned like multiple metrics and then ask you to implement them, and then I forgot that we have not so much time. So please remove this line in 180, like this one. So leave it as this without that if condition, and if you remove that if condition, then you will successfully be able to train it for multiple epochs. And also you can run this in Google Colab, I think, if you upload the dataset. So I'm running this on CPU. So if you return back to the task, let's just double check for those following. Is the task 15.3, I think, yes, understandable? Plus, minus, just to see if somebody is alive there. So we need to modify the code that we used so far to have the arithmetical addition, not the concatenation type of the model. Should not be that difficult, hopefully. Meanwhile, I will also update, well, I will update the template that I gave you in the very beginning and remove that line that should not be there. 180th line, I think, or something around that place where there's NIN, so it should not be there. So great that some people are finished with the first task, even though I had that misfortune of having the wrong equation, and that's really great that Christopher's caught it and were able to fix it himself. So that's really great that you understand what you are actually coding, not just copying exactly from me. So I updated 15.2 task just to make sure that there is no bugs for others who will try it later. 15.3 task is not yet completed. I see that Christopher's is getting it. So please, if other people are not getting it, what there should be done, then post a minus. Then I will explain it. So, and if I look at the training results, so the training is proceeding good. It's reducing the loss function, minimizing it, and having a little bit better predictions of the lungs. Okay, so I'll let you a few minutes to try to complete this task yourself. Hopefully I did not make mistake this time. Of course, so I can tell you ahead of the time, you need also to change the initialization part of the model. It's not, as I said, it's not just like changing the concatenation to the addition. You also need to think about it a little bit, what you actually add there. Yes, I see first people publishing the results. So this is Christopher's again, the first one. And we have also Everts doing good. And in the second task, the Everts was the second person, and then here the Christopher's is the first one. Let's see who is going to be the second one. And yeah, actually, I really got interested about it, that dilated convolutional part. Was actually, I need to read up. Is it actually like what was the progression of the papers? Like, is it like Deep Lab, then there is UNet 3 Plus, and like which one of them are more grounded in some kind of reasoning why actually that would work better or not? That's really good point. Thank you for that. Dilated convolutional or UNets or stuff like that. Also resonance, basically. Yeah, so thank you for that. That's a good point. So let's see. Then yeah, let's try to change then the model using the new equation. So the parts that we need to change are quite simple ones. I will show the code. So of course the concatenations now become the additions. So, and then if we have the backprops there, okay, cool. I see there's Janis is giving some references. That's great. I also looked up some references while you were doing the code, and it seems promising. Of course, I tried dilated convolutions. I just like not specifically thought that they would be beneficial for semantic segmentation, but need to look up on that, and maybe you're totally right. Maybe I'm missing some part of this. So here we changed all of these things from concatenation to addition, right? No problem. Then the problem arises when we need to concatenate different kind of channel count, right? So we need to fix the channel count issue. That is not too difficult, hopefully. So the channel counts now we have, so we can actually look at this. So out 5 comes from conv middle, that is 64. The 4 comes from down 4. So there's no problem in this line. Then the next line out 3 comes from down 3. Down 3 produced 32 channels. Then the out 6 comes from this guy of the out 4, except here there is a problem. So out 5 will produce as 64, but there is 128. So this should be 64. I think then the next one should be 32, then the next one should be 16, and then the 8. Hopefully, if I run now the debug, there's not going to be error. If there will be, then I miscalculated something. No error. So this time I did not miscalculate it. So yeah, very easy conversion. At the same time, need to think about it a little bit. So one interesting experiment would be to compare both of those to see which one works better. That would be a really interesting experiment. The other thing that of course you can use is to implement the weighted cross-entropy, binary cross-entropy, not just the simple one. So you know the number of pixels in each sample that are the long pixels and non-long pixels. Then you can calculate the ratio and use that as a weight, and that can improve your learning as well. So now it's training. We'll see what we get. Hopefully something good, not bad. Of course, on the GPU it will work much faster, but this is really small dataset, so yeah, not too bad. Looks about the correct. So this is working now. Then the last two things. So if you go back to the Jamboard, there's actually, like, especially for semantic segmentation, there are so many types of loss functions. I think also for instance segmentation. This is actually, there was one GitHub where you can see the map of all of the loss functions for the semantic segmentation task. And I think we could try out to do also another loss function, at least one of them. Just quickly try to find the map of those loss functions, and maybe I can also later share the reference to the GitHub. Somehow forgot to add that one beforehand. So if I add it, so some of those loss functions we already know, some are new ones, so I will add here. And often, especially in all of those semantic segmentation, instance segmentation, and so on, you combine them together, but you most likely combine them together by different class of loss functions. So we already know the cross-entropy and binary cross-entropy and all of those, right? And so there is one from, I think that was from the Facebook or Google, the focal loss. That is quite important addition that gives really nice results, that is not derived from the information theory, but like achieved in experimental results. So then there is the IOU. You can use this directly as a loss, but in most cases this is used as a metric for the evaluation, how good is your output. So the evaluation of the IOU is just by looking how many pixels that you want to have in your ground truth and your predicted area match. So you can match the area and see what would be the so this you could think of this as a percentage, but it's like just matching the area. So just a second, trying to quickly find some example of that. Actually had that one ready, somehow lost it. Just a second. It got a little bit sidetracked because of that bug in the code there. So here, the IOU that you probably used, you use this in most cases for as a metric, not directly as a loss function, but you could use it also as a loss function. Then another thing is very important in this is the dice loss. I think okay, here we have the dice. So the dice is actually the same equation as for F1 score, if I'm remembering correctly. And that is something that is commonly used. So one of the common loss function combinations that you can find is focal loss plus dice, and quite popular combination. In general, a lot of these loss functions have they are useful because they have quite significant impact on the results. So you can play around with your architectures and data, but you can also play around with the loss functions. So this is going to be the loss function of dice. So what I would like you to do as a last task, and maybe I will also put this task as a homework actually, would be to combine the binary cross-entropy loss with the dice loss, and then train on that one. So you have the composite loss function that we already talked about, those. So you can have binary cross-entropy plus the dice. You can have also, of course, some coefficient there. Dice, so there's BC. coefficient. So let me give you that small equation. So yeah, so you could implement at home this one, and also I will give you the equation formally for the I of u. So your homework going to be to implement the dice loss, to add that to the binary cross entropy, and also calculate the metric of I of u that you're going to use alongside your loss function metrics. So that could be one direction of thought. I will also add maybe some interesting data set that you can work on. And the next time we'll look at the instance segmentation tasks. So remember that I talked in the very beginning that the instance segmentation tasks will have kind of bounding boxes, and there are actually two types of like large families of instance segmentation tasks, but we'll try to look at the simpler ones. So that's about it for today. Hopefully it was fun. I will add the homework for these loss functions and the metrics that you can add as well. And so this is like your first step in direction of all sorts of segmentation type of models. Next time we'll look at another segmentation type of model, and then afterwards, so all of these workshops in this format I think will go till the end of February, and the next time we'll look at next time after the instance segmentation we will look at the RNNs, so recurrent neural networks, because some of the students who are working with me with research need recurrent neural networks, and at the end I think we'll look at one of the reinforcement learning algorithms, because at least one student is working with reinforcement learning. So that's going to be quick wrap up with all of those quite popular techniques that you can use for your research, and hopefully you will succeed with this, because there's not much time left for submitting the thesis, and yeah, but we started in beginning like I don't know, like we started at the end of October I think, or something, so that's a good progress that we got so far. So yeah, let's speak with you next week. Thanks for joining, and keep submitting the homeworks, right? Bye bye.